right, so for the difference for 11.4, we start addressing everything that we learned with geometric series, and we now say, what about infinite ones? So we've had finite, which means a set number of terms. You could count them up, you could bracket it off, we could plot it on a coordinate grid, and we could say it's just these values and we're going to add them up. And it's been able to give us a number for it. So what happens when we have something that is infinite? Meaning you have a summation and it says you're starting at 1 and you're going to infinity. When we're dealing with geometric series, let's look at this. We have our first value, and then we have our r value raised to an exponent, n minus 1. Since we have this exponent, we have an exponential equation. So exponential growth or exponential decay, doesn't this look very much like our exponential equations? When we had our first term, we had our base, and it was raised to our x value. That's all this is. This is why we learned our exponential equations first, and we learned our logarithms first, because all we've done is just rewrite it with a different term that relates a little bit differently. And so we still have our base, which tells us our growth rate. And here we had our ratio, which tells us the growth rate, like how are we getting from one to the next? It's the exact same thing. But when this goes to infinity, we don't have a stopping point. We know that our exponential growth equations graph like that. And so we're going to go to infinity, higher and higher and higher and higher. Would we ever be able to add that up? Because our numbers are going to increase over and over and over. When you have a geometric series that is infinite and your base rate is a growth rate, what do we know about growth rates from our previous chapter where we studied exponential growth and exponential decay? We know that growth rates are always greater than 1. Because we start with 100% of what we have, right? We started with 100% and then we're adding to it. So when we had that, we had our rate, or that we would often say our B plus, and then we were dealing with a percent. We were adding a certain percent, maybe compounded a certain number of times. So when we're adding something to it, it made it bigger than 1. So anytime our value is greater than 1, we know it's growth. What we can deduce from that is anytime our series has a rate or a ratio that is a growth rate, meaning it is greater than 1, you will not be able to sum it up. It will not have a number that it will come close to, because it is forever going up and our numbers are getting bigger and bigger and bigger. Now, let's address the ones that we had whenever they were decay values. Okay, so when we were looking at decay values and we were looking at a graph of a decay value, we said it looked like this, and it got smaller and smaller and smaller. We also said that our decay values, our B value had to be somewhere between 0 and 1, meaning that this B value is a fraction as we understand a fraction to be, so a fraction less than 1. Okay, and so what we did in class is we tore up a piece of paper into smaller and smaller and smaller and smaller pieces. And I said, if we kept adding those pieces, if I started gathering, if we gathered half a piece, and then we gathered a quarter of a piece, and then we gathered an eighth of a piece, and a 16th, and a 32nd, and a 64th, that these pieces here actually added up to something. But eventually, everything that we were adding to our bulk excuse me, our bulk part really was negligible. It really didn't have, these pieces that we were adding were so small that they had no effect on the bulk of what we had. So when we have an infinite geometric series where we have a decay rate where our rate is between 0 and 1, we are adding pieces that are so small that they have no effect on some big bulk. And so eventually it does reach some number. And when we graph that, we knew that the opposite of a decay rate, when we were looking at exponentials, opposites are logarithms, correct? And logarithms are graphed like that. And so we have this, we had asymptotes that they would approach in the same way for this infinite geometric series, that we're going to add stuff to it, and then eventually we're going to add such small pieces that it's not really going to change it, and it's going to approach some value. It won't ever exactly get there. It won't get bigger or more. This is an estimate in mathematics. We say this is what it's equal to. We just go ahead and call it that. Okay. And to find that value, we simply take our first term, so whatever the first term was in our sequence, and we're going to divide by 1 minus whatever the ratio is. Because we started with a whole piece, and we've got some ratio that we're breaking it up into. That's the way that it helps me remember what it is. So I start with a 1, and then I'm going to divide it up into a whole piece that's divided however the ratio says I need to divide it. And that's going to give us a sum of something. So let's look at this one. If it tells us to find the sum of this series from 1 to infinity, we know because it says infinity that it's an infinite series. So the very first thing that we have to decide is, can we even find a sum? So to find a sum, we know that our R value must be between 0 and 1. So the first thing that we're going to do is we're going to look at our equation that gives us the different values of our sequence. And we know that it's always written A times R to the n minus 1. So 3 must be our A sub 1 value. 0.7 must be our R value. Is 0.7 between 0 and 1? Yes, it is. Because it is less than 1, we can go ahead and find the sum. If we had 3 times 7 to the I minus 1, you would say there is no sum. It cannot be found. Okay. So now that we know those two things, we know that A sub 1 is 3. We know that our R value is 0.7. We simply plug it in. The sum of this series is our first term, A sub 1, which is 3, divided by 1 minus 0.7. So that's always going to give us a number less than 1 on the bottom. You should always have a number less than 1 on the bottom. And we could rewrite that as 3 divided by 1 third. It's not even 1 third, or 3/10. Let's do it that way. 3 divided by 3/10, which equals 3 times 10 over 3. Those cancel out, and we get 10 there. And so when we add this one up, all of the pieces add together to be about 10, and then it's negligible from that point forward. Okay, so let's look here. If we were going to find the sum of this series, the things that we need to know for the sum of the series is what's our first term and what is our ratio. So our first term, we know that it would be 1. That's where we start. And what is our ratio? How do we get from 1 to 1/4? Or negative 1/4? How do we go from negative 1/4 to 1/16? Well, we have an R value that's going to be raised to an exponent. It looks like we're multiplying times 1/4, right? However, we have our sign. It's going negative, positive. Oops, and I wrote that wrong. My bad. Negative, positive. When we go back and forth between negative, positive, negative, we know that our value is a negative 1. So we've got a negative 1/4. So now we have everything that we need to plug in. We know that the sum of that series is going to be a sub 1 divided by 1 minus whatever our r is. Our a1 is simply 1. 1 minus, use parentheses if need to so that we don't lose those values there. Okay, so I've got 1 divided by 1 plus 1/4, so I've got 5/4, so I've got that fraction on the bottom. And I need to correct myself on this one. I said you're always going to have a number less than 1 on that, and that is not correct. Sometimes, in this case, depending upon how you are jumping with your r's, we actually had a number less than 1 on that because we took away more. There were chances we were actually taking away some instead of adding. So I'm corrected on that one. Okay, so again, we can find any unknowns with this equation. If we know the sum, we can plug that in. We know the sum in the first term, we can solve for r. If we know the first term in r, we can solve for the sum. If we know the sum in r, we can solve for the first term. So we can rearrange our equation in a lot of different ways. We have all of the tools in our tool belt that we need to solve for any of the unknowns that we have there. So the thing that you need to know for infinite series is to be able to use this equation to find the sum of an infinite series and whether or not that sum is actually even valid, right? So then to address the end with let me see. So 11.5, let me send you another one.